Hi everyone, welcome to another part of lecture 2, and we will continue with the multiplication rule. Okay, so just before going to details, just remember the last example, the aircraft example. So in this example, if you remember, we calculated some probabilities and some conditional probabilities. And in here, in this example, if you remember, we first calculated, or we are given the probability of an event, and then also we said that the probability of B, this is B given A, right? So intersection of these two events, that's mean the event A will be occurred and event B will be occurred. Okay, so this part. What we did here, we simply multiply the PA and PB given A, right? So that the results of this multiplication give us the probability of occurrence of the A and occurrence of the B. So by using this piece of information, we can generalize this this multiplication and for the n events, okay? And we call it multiplication rule. So here, assume that all of the conditioning events have some positive probability, and let's say we have n events. The intersection of these n events can be calculated as probability of A1, the first event, times probability of A2 given by A1, and times probability of A3 given A1 and A2 is intersect. So this is simply like something like that. Let me open a new page. Okay, let's say this is our starting point, and let's say A1 is a Q, and then there is two options, A2 and A2 complement. This part here is this part means that A2 will also be occurred. Okay, so as we did in the aircraft example, we will multiply this thing, right? Like A1 times A2 will give us the results of the probability of occurrence of A1 and A2. And now imagine that there is another event here, and let's say this is a A3, and also we have A3 complement, right? So this path, let me change the color. This path here, so here is the probability of occurrence of A1 and A2 and A3. So we can do the same thing, right? A1 times probability of A2 given A1 times probability of A3 given A1 and A2. So that's mean they have to be occurred by following each other, right? So this is the main logic behind the multiplication rule. So let's go back to slide. To prove this one, okay, so let me let's go from here. To prove this one, this is A1 times probability of A2 given A1, the probability of A3 given A1 and A2, and until the last one, the end event. And this will be probability of AN given the intersection of n minus 1 event. Okay, so if we rewrite this multiplication such that by using the conditional probability definition, this part is this one can be written as probability of A1 and A2 divided by probability of A1, right? This is coming from the conditional probability definition. And the same thing we can do here, right? here, because this is a one event and that is a one event, and this can be written as the probability of A1, this is an one event, as we did like here, and this 2 is one event. Okay, so this is the probability of A1 intersect with A2 intersect with A3. And also we can divide this term to probability of A1 and A2. This is the second event here. So if we extend this multiplication until the event ends, we will finally get this one, right? Because this were each other's. And finally, we will get this one. Okay. So this is the multiplication rule. So let me give you an example. Let's say we have a deck of cards. Okay, there's a 52 cards, and we will draw 3 cards without replacement. The meaning that the without replacement meaning that when we draw a card, we will not replace them, and then we will draw the second card. Okay, so that's mean in each draw, the number of cards will decrease by 1. Okay, after the first drawing, the total number of cards will be 51, and after the second draw, the total number of cards will be 50. So we wish to find the probability that none of those 3 cards is a heart. Okay, so that's mean the probability of getting some other cards rather than the hearts. Okay, so remember there are 15 hearts in 52 cards. Okay. So there's an okay. So let's give some piece of information to calculate the probability. So we assume that at each step, because we will draw 3 times, each one of the remaining cards is equally likely. Okay. And by this method, this implies that every triplet of the cards is equally likely to be drawn. So these are the disjoint events, and each card is equally likely. So what can we do here? So there is a way to calculate this probability is that such that we can count the number of all triple cards, and we can pick the ones which not includes a heart, and divided all the possible card triples. Okay, so I mean we can simply create an event like, let's say A, and that will include 3 cards. Okay, let's say, for example, I'm not sure, but let's say there's a X. Okay, X number of X card triples can be created, let's say, and my second event will be again the 3 cards, and these will not consist of any hearts. And let's say this is the Y, the magnitude, not the number of the cards triples. So we can simply calculate the probability. Remember the uniform model and the disjoint events, and we can simply calculate this as Y divided by X, right? Okay, now instead of doing these things, let's define the events AI. The I card is not a heart, and I will be from 1 to 3, because we will draw 3 times, right? Okay, let's make it concrete. So this is the first one. This is the first event here, and let's say this is A1. And this one is A1 complement, right? So let me change the color. And let's say this part is A2, and this is A2 complement, this part, right? And let's change the color again. And let's say this part is A3, and this is the A3, sorry, A3 complement, right? So by using the multiplication rule, remember that we want to calculate the A1 intersect of A1, A2, and A3, right? So remember the multiplication rule. We want to calculate the PA A1, this one, times this one given A1. That's mean A1 is occurred, and then A2 will be occurred. And this is the second term we will calculate. And let's look at another one, the last one, this part. That's mean A1 and A2 will be occurred, and this information will be given to us. We are given that A1 and A2 is occurred, and what is the probability of A3? So simply we can say that probability of A3, given we know that A1 and A2 is also occurred. So if you just put the number, there is as I say, 15 cards first, right? So this numbers is coming from, and there are 39 cards, they are not hearts. So the probability of A1 in the first row will be 39 divided by 52, and times 38 divided by 51. Why? Because we draw with replacements. Sorry, without replacement. Okay, so there will be 38 cards. They will not include any hearts, and the total number of cards will be 51. And the same thing here. There will left 37 cards, and among them there's no any hearts, and the total cards will be 50. And approximately the probability of this will be 0.4135. Okay, and this is the probability of this path. So this is a multiplication rule, and you can extend this multiplication for any number of events. So we are going to use remember this multiplication rule, and we are going to use this for the total probability theorem. So in this theorem, let's say the A1 until N, let's be disjoint events. And these events form a partition of a sample space. That's mean the union of these events is the total sample space, like omega. And assume that each event have the positive probability. So then for any event B, we will have the probability of B will be the probability of A1 intersect B plus A2 intersect with B plus A3 intersect with B until the probability of AN intersect with B. So we can rewrite this one like this one, right? Because remember the definition of the conditional probability. Let's say the probability of BA1 is equal to probability of A1 intersect B and probability of A1. So this term is the multiplication of this two term. So we rewrite this part as this one, right? And we can do this for any kind of events, any events. So, okay, so we can use this theorem to solve the complex problem. Because why we use this? I mean, how this theorem can be useful. So I can say that maybe the events B can be complicated, and the events A1, the smaller events, will be might be much easier. And by using these easier events, we can calculate the more complex events B. Okay, so let's first illustrate this this multiplication and how that works. Let's say this part is A, and this part is A1, this part is A3, and this part is A2. And let's say this is the event. So from this one, from this illustration, how can I define this part? This part. This is simply the A1 intersect B, right? And let me change the color. And this part, simply the A3 intersect B, right? And finally, this part here, this is an A2 intersect B. So let's say there are some points here, and I just want to pick one, okay? And I mean from the B, okay? And I'm gonna ask you what is the probability of that chosen points, sample points, belongs to A1 from this point. Like there are some, some points like that, okay? And let's say I randomly choose one of them, and I'm asking you, what is the probability of this points is belongs to A1? So what is the probability of this part? Let me change the color again. So this part, what is the probability of this part? The first one, let's probability of something. The first thing we know that, so we know that these points are coming from the B, right? So that's mean we are given B. We know that piece of information, right? And I'm asking this one, right? What is, I mean, this is the mathematical representation of what I'm asking you. So what I ask, I'm choosing a point, and that point belongs to B. And what is the probability of that points coming from the B is also belongs to A1? So I'm asking simply this one, right? P, probability of A1 given B. So how can I calculate this from the conditional probability definition? I can say this is A1 times B divided by probability of B, right? So simply, I'm gonna take this region and divide by all B, okay? So the logic is coming from this point. So for this sample, let me clear my board. Okay. So here there are three events, right? A1, A2, and A3. There is no any other possible things because these are the partition of the sample space. This is my omega. And after A1 happened, and if that is information is given to me, there are two things right here. The first one is it can be this part and this part. And also B complement. What's the B complement here? And this part, right? This part is B complement. So there are two possible events. There's one, B complement and B. And what was the B? We define it. This part is the A1 intersect with B. So, okay. And same thing others. The second events can be the A2, this part, this whole parts. And after this happened, there are two possible things. The first one is this part, and this part is A2 intersect with B, right? And the other part is here. And what was here is the B complement, right? Because B is only here, and B complement is here. When we are given the information of A2 is happened, okay? Because the actual B complement in whole sample space is all this white region, but we are looking only, sorry. We are only looking this part, okay? Why we are looking only this part? Because the information has information of the A2 is given to us. And same thing for the A3. And if you want to calculate the B given A1, right? So sorry, A1 given B. So let me check. Probability of B given A1 is simply multiplication of the A1 and A1 intersect with B. So, okay, let's make it more concrete with an example. So let's say you enter a chess tournament and where your probability of winning a game is 0.3 against half of the players. Let's say, and this is a type one, the hardest one, the hardest players. And the second one, the probability of winning a game is 0.4 against a quarter of the players. And these are called the type 2, and maybe these are the medium players, medium level players. And the last one is the 0.5. The probability of winning a game is 0.5 against the remaining quarter of the players. And let's say these are the type 3 and the easiest players. So you play a game against a randomly chosen opponent. And what is the probability of winning? If you are giving the information about your opponent, you can easily calculate, and also you are given. But if I randomly choose it, how can you calculate this thing? So here, let AI be the event of the playing with an opponent of type I. Okay, so we have A1 is 0.5. These informations are given to us. A2 is 0.25 and A3 is 0.25. And also let's define the event B. Okay, and this is the event of winning. And we know that we have the probability of B given A1. So if your opponent is type 1, the probability of winning the game is 0.3, right? And if your opponent is type 2, in this case, the probability of winning a game is 0.4. If it is a type 3, the probability is 0.5. So, and the ask probability is the probability B, right? The probability B. Let me draw this one. Let's say draw here. So let's say let's say this is type 1, this is A1. and this is A2, and this is A3. Okay, so these are the probabilities of having an opponent from each types, right? And let's say this is the P, winning the game, the probability of winning the game. So the event P is the win event of the winning. So we are asking, we will randomly choose a point, and we need to calculate the probability of winning the game, right? So if, let's say these are, I mean, there are some points in this omega. If I choose an opponent from this part, for example, it will be from the type 2, and I will not win. Okay? If I choose from this one, it will be from type 1, and I will win. Okay? If I choose this one, the opponents will come from, or the opponents will be type 3, and I will not win. But if I choose from this one, the opponents will be type 3, and I will win the game. Okay, so this is the logic behind this total probability theorem. So let's forget about all this multiplication, but just try to understand the logic. Okay, so let's say this part. So what is this part? This is A1 intersect with B, right? And this part is A1 intersect with, sorry, A2 intersect with B, and this part is A3 intersect with B, right? So I need to calculate the total probability. So that's mean the sum of this part, right? Sum of this part. So I can simply write that, and probability of A1 intersect B plus probability of A2 intersect B, and times probability of A3 intersect B. And remember from the definition of conditional probability, how can I rewrite this part as simply the probability of A1 times probability of B given A1. Okay? What was the definition of probability again? Well, it's simply the probability of A1 B and probability of A1, and multiplication of this two term will give us this part, and I'm looking for this part. So I know this probability, I know this probability. These are the given to me, and that was for the type 1. It is 0.5 times 0.3, and same thing for this. And all these numbers are given to us. So 0.4 times 0.25. So 0.25 times 0.4 for this one, and times 0.25 times 0.5, and this will give 0.375. And this is the probability of choosing an opponent. This is the probability of winning the game against the randomly chosen opponent, and this is the probability of this part. Okay, I hope this is clear and you understand the logic behind this theory. Again, please don't memorize in formulation. Okay, maybe just a simple one like this one from the definition, and then you can derive all this multiplication and other rules from using just simple one formulation. and just try to understand the logic. Okay, all these formulation are given to you in exam or any other places. So that's why it's important to understand the logic behind all this theorem or some mathematical things, some properties, etc. Instead of memorizing, just try to draw some. First, try to draw some the given problem, and then it will be easier to solve it. Okay. So thank you for watching. I will see you in another part.